Faults are important geological structures and we can identify them on geological maps. But sometimes it takes a bit of detective work. We're going to take a tour of Scotland looking at some faults on a variety of geological maps. Let's see if we can find the faults, but then let's also see if we can understand which way they've moved and how they've disrupted the surrounding geology. Well, let's start off with this one here, which is for southwest Scotland. And let's just zoom in on a little bit of it up here in the north. So we can identify a fault on this because there's a radical change in the geology. Let's just have a little bit of a closer look. Well, there's a clear break on this map, isn't there? Running from here, from the northeast down towards the southwest in this sort of direction, where you've got these sort of lilac coloured rocks, lavender coloured rocks here. It's studded through by the red, little streaks of things in here. Well, the reds are granites which are punching through these rocks in here. But on the northern or the northwest side of this contact through here, a radically different set of rocks. And this is a fault. It's actually called the Southern Uplands fault. So faults like this are pretty easy to spot because they separate these two radically different types of geology. If we zoom in a bit, we can actually get an idea of the orientation of this fault because it chops across the landscape, running across the valleys here without V-ing in, suggesting this is a very steep structure. Whereas over here, you can see that these sedimentary contacts, which are Devonian sitting on Silurian, follows the valley systems in here, the valley in here and these valleys. So these sediments are essentially rather gently dipping. So we have relatively gently dipping strata and a steep fault chopping them. Well, this map is pretty regional. To give an idea of scale, these grid lines in here are about 10 kilometres apart. But it gives us a good idea of the context for the Southern Uplands fault running across the map. And it's separating the Southern Uplands from the Midland Valley Basin, which occupies most of the central belt. But let's put that slightly more in context then by putting the next map north. And if we cross the Midland Valley Basin and past Glasgow, we end up with a major structure here which separates the Midland Valley, the central belt of Scotland, from the southern Highlands. Well, let's zoom in onto this area up here. So this is the Highland boundary fault running here, separating the old red sandstone here of the Midland Valley, which are Devonian in age, from the metamorphic rocks of the southern Highlands. So let's go down here and have a look at an ancient map for the Loch Lomond area. This is a really beautiful map. It was published in 1901 and is actually hand coloured. And here is the Highland boundary fault. So we can trace the fault zone coming down through here, across Loch Lomond, clipping the islands. The fault zone itself is decorated by these slices of strange material. Collectively, this is the Highland border complex, which are exotic rocks caught up along the fault zone. But overlying the fault zone and the Highland border complex is this patch of pink material, which is Devonian in age, associated with the old red sandstone. So this fault zone and the Highland border complex are sealed stratigraphically by these strata. And this indicates that this fault zone was active before these rocks were deposited. So we can put an age on the fault zone. Well, what about its orientation? Well, the fault comes out of the high ground here and comes down to the shores of Loch Lomond and through the islands, but basically stays on trend through this landscape, indicating the fault is again a steep structure. So the Midland Valley, which occupies the central belt of Scotland, is bounded by two major faults. Both of them are steep, but both of them are very large. And it's their size, in terms of displacement, that presents a problem to us because we've got no markers we can use to see the sense of movement. We know they're steep, but we don't know which way they've moved. Are they dip slip? Are they strike slip? How have they worked? Well, let's go off into the Southern Highlands now and have a look at another fault structure where we can indeed get an idea of the sense of displacement. Well, this is another old map. It was published in 1902, and again is another hand-coloured version. Worth pointing out the scale, the width of my thumb is about 1 kilometre. It's the same scale as the Loch Lomond map that we've just been looking at in detail. Significantly more detailed then than those regional maps we used to look at the extent of the Highland boundary fault and the extent of the Southern Uplands fault. And we can see some really neat structures on here. Running across the map is a major discordance, and you can see that these features in here, these blues are metamorphic limestone sequences or limestone rich sequences, and you can see that they're quite complicatedly folded in here, and these folds are abruptly truncated and apparently moved down in this position here. So we have a fault running through here, through the Southern Highlands, that's offset previously folded and deformed rocks and moved them down so that this northwest side has moved down in this direction, which is a left lateral sense of movement. And everything's been offset, hasn't it? You can see that these pinker rocks in here have also been offset. So an example of a pretty major fault in here that's moved, it's moved left lateral, offsetting previously developed structures. Again, it must be a pretty steep structure because there's quite a lot of topography here in the Southern Highlands, and the fault just runs straight from valley over ridge line into valley and back over the ridges again. So it's chopping right across the landscape, presumably as a steep structure. Well, it's perhaps no surprise that we've got faults within the Highlands of Scotland, but let's go down into the central belt again. Well, let's look at this map here. It's amazingly detailed. Same scale as the last one we looked at from the southern part of the Highlands. And these grid squares in here are a kilometre again. And basically what you can see on here is enormous detail. It's from the southern part of Fife, from central Fife up here in the northern part of the map. And there's some pretty spectacular detail in the mapping in here. And you can perhaps appreciate why if we just have a look at the key. So these are generalized vertical sections, and they show the stratigraphic order and the detail with all these various coal seams in here in the various levels, and important marker bands, which are these marine bands in here as well, that provide a correlation framework so that the miners, when they were working underground, knew which coal seam they were in and where it may continue and what was adjacent to it. So all this detail in here represents coal seams. Clearly, at the time this map was made and before, it was really important to understand where the coal seams went so they could be exploited carefully into the subsurface. And again, we can get an idea of some of the complexity in here by looking at the cross sections down here. Well, these faults aren't very big, are they? Let's just think about how much movement there is in terms of the offset of this blue horizon, or packages of horizons in here, down throwing towards the left. It's not very much. But if you look at the amount of throw on the faults compared to the thickness and the spacing of the coal seams, that's really significant, because you may start on one coal seam across here, and if you kept going and didn't realize there was a fault, you'd cross into an entirely different structure. And here you may just continue across into a unit that had no coal seams at all. So understanding the faults and their detail was really important for the economic development of this area. But there's more to it here than just faulting. There's folding as well. And the faults are chopping around the folds, and we can see this on the map. But let's look at this area here and zoom in. So we look at this map, we can see that the layers come around a structure, so there's some kind of fold through here like this. Their youngest rocks are in the middle in here in the core, and they're symmetrically disposed around this core, so we go from light green into the light blue, dark blue, and into the olive green at the sides, both sides in here. So we've got a fold structure. but look more closely and you can see it's cut by fault structures. Let's just look at this area in a little bit more detail. Let me just put my stick across the fault here. And it looks like this layer here has been offset the northern side towards the east, on this side of the fold, and on this side it's the opposite sense. The northern side has been shunted to the west. So it looks like this fault's moved both east and west. Well, clearly that hasn't happened. So how do we explain that map pattern? Okay, let's just try and draw this as a little three-dimensional block diagram. So we'll start off with a map view, something like this. Okay, and let's put a fault on it, coming through here like that. Right, let's turn this into a block diagram. So we've got the side view here, something like this, and a side view along here, like this. And we'll pop the fault on, dipping in this direction, fairly steeply, like that. Now let's draw on a fold. So we'll have the fold trending in this direction. So we'll put a bed in like this, and let's just say it comes around in the subsurface like that, and out again. And we'll just make that slightly more three-dimensional, make a layer like this, make it come around in the subsurface. So it's a synform, or so it's a syncline, something like that, for a layer folded in the hanging wall to the fault. I'm just going to draw on a bit more fault in here now, just so we can see where it goes. Something like that in the subsurface. Just tidy this around a bit so we can see the edge of the box coming through like that. So that makes it slightly more three-dimensional. And I'm just going to draw in where this layer would go, something like this, against the fault plane. So there's our fault plane coming through with our layer in that sort of shape. Right, well, let's say that this fault has moved, so this side's down and this side's up. So if there's a fold here on this side of the fault, well, like this on this side of the fault, it's been carried up on this side. So let's just draw in the fold on this side. So this point, the fold would be here, coming up to the fault plane like that. Oops, let's tighten that over like something like that. So there is our layer seen through the fault on the other side of the fault, and the beds on the other side would go off like this. Okay, something like that. Now, what I'm going to do to help the visualization of this now is to continue our block diagram, but show a little bit that's been eroded away up in the air, if you like. So I'm going to extend this side up a bit like this, and draw our block a bit further along. So in other words, we've got a sort of step on our landscape. Okay, so there's our block. And what we can do now is draw the rest of the fold up. So this layer will come up like this, like this, like this, to make the fold. And you could imagine on the back wall of this, it would come round something like that. So that is our pattern of our structure through here. I'll just colour it in. So that's our map pattern. Let's just colour in the profiles that we can see at the end of the diagram. Something like that. So we've got the end wall of our model in here, the syncline coming through like this, offset by the fault and continuing through there. That's not a fault, it's a step in the landscape. The hinge line goes through. Well, let's draw a hinge line and shade in the inside part of the fold to make it a little bit clearer. So here's the hinge line coming through this side of the fold structure in the coming through here like this. That's an arrow, and there's the trace of the syncline over here, and I'll just draw it coming through here, and it would come through here like this to here on this side of the fold structure. Okay, so there is the syncline coming right through, and we can see that the intersection of this hinge line with the fault plane on this side is here, and here on this side of the fault plane is just there. We'll come back to those in a second. Let's just add some shading just to bring out the folds a bit more clearly, so we can see that this layer is going to come around something like this, in here like this. Let's just put this like this so you can perhaps see the shape of the fold rather more clearly. There we go. So there's our fold coming through. Put a bit in here as well. Coming through something like that. Remember, this is just a bit of landscape up here, so let's just cover it up because I don't want that bit of map pattern to confuse. We just used it to illustrate the shape of the fold going off into the footwall of the fault. So that's the map pattern we're trying to explain. Narrow outcrop width, wide outcrop width between the two layers from limb to limb, from this fold structure to this one here where it's offset across the fault. And it's simply a result of seeing different parts of the fold profile depending where they've been cut by the landscape, having been offset by the fault. The thing that gives the displacement on the fault is the offset of the hinge line. This is a so-called piercing point where the hinge line here comes in from this side, has been offset on the fault and dropped down onto this side. So that is the displacement direction on the fault plane and the amount of displacement. So these offsets that we see in map view are only an apparent offset. The true offset is not strike slip, moving in this case left lateral, in that case right lateral, but actually it's dip slip, and the map pattern is a result of the fold geometry being offset by the fault displacement. So we can explain the map pattern then simply by a fault that's quite steeply dipping like this, which has downthrown this side, so we see more of the syncline on this side of the fault than we do on that, which explains why both beds are seen wider apart on this side than on the north. It's a classic example of a faulted fold. To see what would happen if the fault had moved as a strike slip fault, I'm just going to put some card on top and redraw the fold in and see how the offset works. So that's looking into the footwall of the fault structure. So there's our fold geometry, no fault movement yet. Let's put some strike slip movement on, we'll make it right lateral. So that would move over here. And you can see what happens is that we have not changed the outcrop width of the fold. The distance between these two tracks on the same limb here are the same across the fault. The hinge line has been offset. Everything's moved in the same direction. We can do the same going the other way if we like, something like that. And we can see the hinge line of the fold has been offset, as have the two limbs, by the same sort of amount. So we can use these outcrop patterns to tell us quite a lot about the displacement pattern on faults. Well, not all faults are quite that obvious on maps. And there's a really major fault system here that we can look at on this map of northern Scotland. And it's here, it's the Moyne Thrust, and it runs all the way down this boundary here, broadly along the western side of this yellowy orange material here, which are Moyne rocks, which are metamorphic, and they've been carried significant distances, maybe over 100 kilometres, over this geology here. Well, this is the northern part of that map, and if we look here, here's the Moyne Thrust. These are the Cambrian sediments. The Cambrian sediments are gently dipping towards the east, and so too is the Moyne Thrust. It's not a steep structure like the faults we've looked at so far. And this makes recognising it in a map pattern rather difficult. We can illustrate it with this map as well, which comes from further south in the Moyne Thrust belt, just south of the town of Ullapool. Here comes the Moyne Thrust, and it's tracking parallel to the unconformity, more or less, that underlies the Cambrian strata forming this grey strip through the map. The thing that's most discordant is the unconformity at the base of the Torridonian, not the fault zones, which is quite an interesting conundrum, except for the fact that they're metamorphic rocks over sedimentary rocks. The map pattern itself, though, is not particularly diagnostic. Well, let's look at a really classic piece of mapping. So this is a really remarkable document. It's a great geological map, and it records really remarkable field work by the Geological Survey in the 1880s. And here's the mine thrust. We picked it in from the north, coming around like this, carrying these yellowish rocks, the metamorphic rocks, over sedimentary, which are these sort of grey materials in here. If you want to see the faults though, in the interpretation, the place to look is in these really remarkable cross sections. They're stuck on end, so you're looking at the side on, but they're major thrust slices that carry metamorphic basement in pink over folded sediments, and loads and loads and loads of detail in here. Well, we can recognise some of the fine detail. Again, it's from the repetition of stratigraphy and the disorder of the normal rock sequence that allows faults to be recognised in this sort of situation. And you can see these yellow stripes, which are a unit called the Saltarella grit, stacked up again and again with the green and the blue in there, making a spectacular set of imbricates. And it's that understanding and that detail of the mapping that allowed the geologists to draw their cross sections and interpret the fault structures. Great mapping, fantastic interpretation, making these wonderful cross sections, and it's all based on really detailed fieldwork by the Geological Survey in the 1880s. So a really classic map there from the northwest Highlands. And we've seen now on a whole series of places around Scotland some really remarkable fault structures. They're commonplace in Scotland and indeed all over the world. And understanding these map patterns allows us to make sense of their tectonic significance and evolution.